Okay, I know we're going now. Okay, good. Oops. Okay, so yeah, if you can, please turn your homework in today. This question about the spatial frequency, maybe I probably need to look at the problem again. Maybe there was some ambiguity there. I was asking for the grading period and the spatial frequency, and both are, pretty much the same thing. If I did, I'll correct that next time. Sorry about that. Okay, so one thing I want to clear up first is the lab. So I was looking at our D2L site, and so there's 13 students in the class, right? And I think only 11 have signed up. So I put a note there to make sure that you're in one of the groups. So the groups that we have are Monday. Did I say 10 to 12 or 9 to 11? 9 to 11. All right, 9 to 11. Okay. All right, so on the website it's wrong. So I'll change that as soon as I go back. And then also Monday from 2 to 4, right? And then we have Tuesday from 10 to 12. So there were, I think, about 7 who signed up for this period. Can any of those go? And there were 4 here, so I'd like to have 5 max. So can we have a few people go into this Tuesday? Nobody. Let's see. So there's 1, 2, 3. All right. So at least if we have some of the students moved over there. So let's see. Who's Monday in the morning then? 1, 2. Okay. Did you guys move from Monday morning? How about Monday afternoon? Who's Monday? 1, 2, 3, 4, 5. What?
We were in Monday morning too. Sorry.
Oh, okay. So we have 6 here, and then I guess we still have about 4 there, and hopefully the other 3 will go in Tuesday. Well, we have 3 in Tuesday already, so good. All right. Now, so the other thing about the lab, I'd like you to go back and look at the lab handout because I actually changed it at the urging of my graduate student who's doing this. She's actually she has like a teaching thing that she's doing as well, and so she's being evaluated on how she administers this lab. So there is so don't freak out, but she wants to have a little quiz at the beginning of the lab session, and so mainly she would just like you to read the lab prior, and there's a little problem you have to do here. Again, it's very similar to the homework problem where you just calculate what the grading period is with a 0 and 30 degree incident beam coming into the hologram. So let's see, let's make sure on that. So oh yeah, so we have, this is unslanted, so I'm sorry. So it's going to be, it's 30 degree inner beam, but it's plus or minus 15 degrees for the 2 recording beams, okay? And so, again, so that should be fairly straightforward. And again, so in that case, you could just use the grading equation to calculate the period because there's no z component, right? So it should be fine, and you don't really, I mean, you could use the index, but then you would have to, and we're using 633 or 632.8 nanometers. You could use the period. If you use the period, you have to change the wavelength by the period, and you have to put the angles inside the medium, or you can forego that and just do it in air. So it's usually easier just to, do it in air and not have to use Snell's law to correct all the angles and scale the wavelength and so forth. Okay. And then, so we talked about the TE and TM polarization. So which one do we have going on? TE or TM? For optimum contrast in the recording.
I don't know that it's like S or P polarizations. So.
Transverse electric or transverse magnetic. So TE is like S and TM is like P. So is it S or P? All right. So TE is perpendicular to the plane and TM is in the plane. Right? S is perpendicular and P is in the plane. All right. So the way we want it then, if we had it in the plane, then the two polarizations would come in at angles to one another, and the overlap would not be optimum, which is, parallel. But if we had them perpendicular, if the polarizations were perpendicular here, then, when they get to the plane here, they're going to be aligned, and so you get maximum contrast. So you have TE polarization, okay, for that. So she kind of broke it down into little parts here so that you can, she pulled out all the questions out of the text and kind of wrote them out. So it's probably easier this way. All the little steps. They're not really questions, but there's steps in this. And then she prepared a nice table for you. So she did actually a lot of work here. So might as well take advantage of that. And then your plot's going to be like the diffraction efficiency versus the angle. All right. So any questions on that?
So are those questions the quiz, or like when we get there?
No, the quiz. So this is the quiz is answering these two questions here, which I already answered one of them for you. So the other question, again, just use the grading equation. It's probably easier to calculate it before you go to class because you have 5 minutes to do it, or 2 minutes. I'm sorry. So yeah, do it before you go in. And so sine of 15, 2 sine of 15 equals lambda over the period. Okay. Okay. So pretty straightforward. Okay. Any other questions? And everybody has a lab group, right? So, and I loaded this new version of the lab up on the D2L, so you can pull that down and look at it. Okay, so the main topic then for today is looking at the Fourier analysis. Of various optical systems, and in particular those systems that are most relevant to the to holography. All right, and again, the Fourier analysis again is quite useful because it gives a very systematic way of dealing with diffraction theory. All right, and of course, diffraction is really what grading is all about. So, in understanding the Fourier analysis, you can get a great deal of insight. And so we'll have a couple of examples, and we'll maybe look at one or two problems that you may have solved, using ray matching and all this kind of stuff, which was very tedious. And we'll see that there's some very slick ways of doing this with some Fourier analysis. Again, those of you who are not too familiar with this, I know a lot of you from OpSci have seen this several times, but those of you who have not, I would recommend, again, looking at Joe Goodman's book, chapters 3, 4, and 5. I'm going to basically summarize the main parts from those and just go over those so that you understand where we're at. And if you have further questions, please see me and I'll be happy to help you with that. So the first thing we want to do is kind of define the Fourier transform as we'll use it. And again, I'm using Goodman's notation. those of you who use Jack Gaskell's book have a different relation for this. But the Fourier transform is given by this script f g of xy. And we're, since we're talking about apertures, the apertures are not one-dimensional, they're two-dimensional. So the Fourier transforms we're talking about are two-dimensional spatial transforms. And we have an integral from minus infinity to infinity of this function g of xy, and integration kernel, which is the exponential of minus j, which is square root of minus 1, 2 pi times fx x plus fy y, and integrated over dx and dy. So the fx and fy are the spatial frequencies here, and in this case they are x over lambda z, and fy is y over lambda z. So, like in that homework problem, I asked you what was the maximum spatial frequency. It's 1 over a spacing, okay? In this case, the spatial frequency is this is a variable which changes as a function of not only the lateral dimension, but also the distance away that you are from the aperture that's producing the diffraction, all right? And so this relationship that we have here then is just equal to a new function, g, the frequency function of f sub x and f sub y. So again, what we have are, so we have some distance here. We have a x and, we'll call that x and y. So here's x, and this is the fx and fy. All right, so so we're going to go through some propagation or some transformation, all right, which will lead to this Fourier transform in spatial frequency space. And then we also have the inverse transform, which gets us back into the spatial domain. And so this here is the inverse, we call that the inverse of, say, g of fx, fy, and that's equal to minus infinity to infinity, g of fx, fy, exponential, but this time it's of j, not minus j, but j, 2 pi times fx, x plus fy, y, and the integration is over dfx, dfy. All right, and so this then is just going to be equal to g of xy. All right, so it allows us to go back and forth. So if we're here, we want to know what's back here. So for instance, actually, one of my students, Shelby Vordran, just finished a paper where she does this back and forth iteration in order to kind of find out what the diffraction field looks like on this by changing the form of the hologram back in the spatial domain. So again, this ability to go back and forth is very important in a lot of different design functions. Okay, and notice too, maybe from some of your other Fourier transforms, a lot of them have a factor of 2 pi sitting out in front, scaling factors. So in this, the nice thing about this notation is that we don't have to carry those constants out in front in this particular form. Okay. All right. So these are really the main functions that we have, and then there's some relationships that are going to be very useful, some properties of the Fourier transform. And the first one, very simple, but again very useful, is just linearity. And so what this says is that if if I have the Fourier transform of a constant times one function plus another constant times another function, that we can break that down into just the constant times the Fourier transform of each of those. Okay, so things just split apart. All right. Another function is similarity. And this one is very useful for the following reason. So if we have scaling of the variables in one domain, we can transform them into another domain, but we have to be a little careful about how we do that. So if we have, for instance, the Fourier transform of a function which is g of a constant a times x and another constant b times y, so these two here are constants, we can get the Fourier transform from that now is going to be equal to g times the spatial frequency in the x direction divided by a and the spatial frequency in y divided by b. And we also have to scale it by the magnitude of a, b, okay, out in front. Okay, so this similarity or scaling is very important because oftentimes we'll have to do that. We'll have to scale things. For instance, you have a rect function. You know, the rect function is defined for, x equals, when x equals 1, you get, 0. And when x is less than 1, you have 1. But most of the time, if that's going to be your aperture, you want to make it some other value rather than just 1. So if you scale it, then you have to, do this operation here in order to correct it. Okay, another really useful and interesting characteristic is the shift theorem, okay, or the shifting property. And again, this is very useful in various kinds of diffraction analysis. So if we have Fourier transform of a function g of x minus a, so again, we shift it by a constant a, and we shift y by constant b. So those are, again, our constants. We end up with the transform, again, of g. So we have g of f sub x, f sub y. But what we end up with from this shifting characteristic, we end up with a phase shift in this. All right, so we have a phase term exponential in the transform domain, which is minus j 2 pi f sub x a, that constant, plus f sub y b. Okay, so again, this is quite useful because maybe we have an aperture. We'll look at some examples of this shortly. If we have, say, an aperture which is shifted away from the axis in x and y, this is how we can recenter that aperture if we need to. But the consequence of that is that if we look at the transform, we're then going to have some phase shift. Okay, and so again, in dealing with holography, we're talking about waves, we're talking about the field, so we're concerned with what these phase shifts might be. All right. Another useful relationship or property is Parseval's theorem. And what this says is that if we take the transform of the magnitude squared of the function dx dy, so what would this represent, g of xy squared? The power, yeah. So if we look at the power, so what, again, these are all between minus infinity to infinity. If we look at the power in one domain, if we're just doing a linear transformation, which diffraction is, should the power change in the frequency domain? No, it should not. So this just says that power is conserved, really. So we have minus infinity to infinity, but this time we have g of f sub x, f sub y squared dx dy. All right, so again, this is really just power conservation. And this, we won't work with this too much right now, but later when we talk, we're going to talk about the spectra of various sources and looking at some coherence properties that we need to deal with. This relationship will be helpful for that purpose. Yes, question?
Are the differentiation variables?
Oh, I'm sorry. Yeah. Thank you. Okay, so those are a couple of properties that we have. What else might we use here? So a really important one for diffraction is convolution. And the convolution theorem, I guess that's what it's called. So what this says is that if we take the Fourier transform of the convolution integral, so we have minus infinity to infinity, so we have g of a dummy variable chi times and eta in sort of the orthogonal directions, and so we're convolving that with another function h of x minus chi y minus eta d chi d eta. So we're integrating out the dummy variables chi and eta. That this is just equal to the in the Fourier domain, it's just equal to the product of the Fourier transforms of those two functions, f sub x, f sub y, and h of f sub x, f sub y. This is going to turn out to be really handy because a lot of these diffraction problems are integral problems, and instead of having to do a cumbersome convolution, we can just play with our Fourier transform relationships a little bit and just do a multiplication of the two Fourier domain functions. And then we can go back and use like an inverse transform to get back to the function if we need it, for instance, in the other domain. Okay, and then related to the convolution is the autocorrelation. And this is kind of like the convolution of a function with its own complex conjugate. All right, that's what the autocorrelation is. So here we have that the Fourier transform of a function g of psi eta with its complex conjugate, and then we have the dummy variable again, chi minus x, eta minus y, d eta, or d chi d eta. This is equal to the Fourier transform, magnitude squared of the Fourier transform, g of fx, fy. Again, that one's going to be useful for talking about spectra and so forth. And then the last property that we have is the Fourier integral theorem. And this basically says that if we have the Fourier transform of a function g of x, y, we then take the inverse Fourier transform of that function. That's the same as taking the inverse Fourier transform of that function and then the Fourier transform of that function, and that's going to still bring us back to g of xy. Okay, so we can again manipulate these operations really, and end up with what we need to get. So again, these are are fairly simple relations, but very powerful in helping us to reduce the complexity of problems as they appear in lots of diffraction analysis. Okay, so those are just some tools, some relationships, some properties that we'll be using. So let's now look at the problem of diffraction. All right, so the first thing to realize is that, the whole notion of diffraction was really kind of laid out by Huygens, and through his the Huygens principle. So this is the first thing, if you're not that familiar with diffraction, maybe this is the first thing to just kind of internalize, because it provides a lot of intuitive insight as to what's going on. And later what we'll find is that all of the diffraction analysis that we do is just a way of doing a mathematical embodiment of Huygens' principle, all right? So, and we'll get to see that very shortly, all right? So what does Huygens' principle say? Well, if we have a field, all right, so let's say we have an aperture here, and we come in here with some wave. And we want to know what the field is out here. What Huygens said was, if we look at this aperture, or even if we just took the field out here at some point, and then consider that there are a bunch of point sources filling, in that aperture, and then we kind of construct a bunch of spherical waves that propagate from these different points out to some other plane. If we then, connect the interfering positions or interfering points here, we end up with this superposition out here. Of these various spherical waves that originated back here, say at some distance z sub 0 away from that plane. And so we can derive the diffracted field, or the field that results out at some distance away, simply by considering a bunch of point sources filling this or along the wavefront at this location, and then creating a bunch of spherical waves and getting the superposition of those waves out here. Okay, so that's basically Huygens' principle. He did it a long time ago, even before I was born. So anyway, a very powerful idea. And again, it serves as the basis for all diffraction theory. All right, the rest of diffraction theory is really different mathematical constructs to kind of realize this. All right, so again, let's look at this now from a, put this into mathematical form so we can then manipulate it. All right. So we'll start out here. We have some aperture out on a plane that we'll call, again, we'll use dummy variables chi and eta. And we have some distance then to our next plane out here, where we have an observation plane. So here we have an aperture, and here we have the observation plane. Like so, all right, and so we have this distance z between them, and here we have coordinates x and y. So this aperture can be any number of things. It could be our hologram, for instance, all right, which will be the case as we go along. And so now what we have to do here is take a bunch of point sources in this aperture. So let's say we have a point out here, P1. There's, say, a normal to the surface there. Call that n, and this wave then propagates over to our observation plane out here, and we're going to observe what is the resultant field out at P0. All right, so that distance, again, it's the radius of a spherical wave, so we have R O1. All right, so between the observation plane and the aperture plane. And we have also there's an angle then from that normal to that ray that connects the P1 and P0. Okay, so that's the geometry that we have, and so now let's just write a relationship that describes that. All right, for all the points in the aperture. All right, so here we have, say, the field in the aperture plane is u of P1. So again, that defines the amplitude or the strength of all these different point sources that we have. And then we have the propagation of a point source, which is just equal to the exponential of minus j k, our propagation vector, 2 pi over lambda, times RO1 divided by RO1, right? That's just a spherical wave. And this kind of weights the spherical wave, right, by different strengths. So we'll get a distribution there. The other thing, though, is that as we move off at these different angles, we have this obliquity factor that we have to worry about, or kind of a, if we're looking at amplitudes, we get a projection of that amplitude that's a function of this angle. So there's a cosine theta, which is our standard obliquity factor. And then we have to, integrate over all points. So again, we're going to do that in 2 dimensions. And if we have some area here we'll call sigma, we do that integration over that area. All right. And then there's also there's a scaling factor too that we have to throw in there in order to make things right. And then this is now going to be equal to the field out at u of P0. So what we have then is the superposition of weighted spherical waves, okay, adjusted for this obliquity sort of projection that we encounter. And then that gives us the overall resultant field at that observation point. All right? So first off, let's see if we could simplify things a little bit. And so first off, if we look at this angle that we have here, this cosine theta is approximately equal to z, the distance that we have between these planes, divided by r01. Okay. So that will help. And then the other thing that we have is this distance r01. So we're going to have to worry about that to some extent, and that's equal to the we could just do a quadratic expansion of that. So that's equal to z squared plus x minus xi squared plus y minus eta squared. Okay. All right. So we haven't really done too much yet, just kind of looking at this, but we want to have a way of actually doing that integral and seeing what happens for a variety of cases and in different domains. So let's make a couple of assumptions. First off, we'll only consider scalar theory. All right, so this is we'll just deal with one field component. And not really worry about the vector nature of the field that we have. And another approximation that we'll make is that RO1 is going to be much, much greater than the wavelength. So that one's not too difficult, to fit a lot of practical situations. All right, so now we have to do this integral, right? This ds, and let's see how we might break the problem down a little bit in order to help there. So we have this this distance relationship here. We can write it in a different form as well without losing any, without actually making any approximations. We can just write it as factor out a z out of this and have 1 plus x minus psi over z squared plus y minus eta over z squared. And so again, so we haven't made any approximations there, but we've written it in terms of the relationship of the size of that aperture, really, because psi is the dimension over here within that aperture relative to the propagation distance. All right. So now we'll make another approximation. All right. So we're going to assume that the dimension in this aperture is going to be much less than z. All right. So what is roughly that dimension? Well, we could say that dimension is roughly the square root of that area is going to be roughly the dimension of it. And that's going to be much less than z. All right. So what that implies then is that x minus psi over z and y minus eta over z is going to be, these values are going to be much less than 1. Okay? So again, this is kind of an important assumption that we're making. And the reason for that is now we have something that looks like a very useful relation, which is the binomial expansion. And this is kind of, the binomial expansion is actually kind of the heart of considering diffraction theory, different regimes of diffraction theory, right? So the binomial expansion is just 1 plus a value b, where, again, b must be less than 1. This is equal to 1 plus 1/2 b minus 1/8 b squared, and then there's other terms moving on out, all right? So we'll make another assumption now, and we'll assume here that we're only going to take these first two terms in our expansion. That gives us basically enough accuracy. And so now we have that R01 is approximately, since we're making this assumption, equal to z times 1 plus 1/2, right? And b is going to be equal to these values here, right? Or actually the sum of those two values. Yeah. So we have 1/2 times x minus psi over z squared plus 1/2 times y minus eta over z squared. All right. So the nice thing that we've done here is we've gotten rid of that square root, right? So that makes this integral that we're trying to evaluate a lot easier. All right. And again, that's really a very useful thing in doing analysis of diffraction theory. Okay, so now let's see where we're at making some of these substitutions. So again, we're going to get rid of that by putting a z over R01 in there. And so that's going to give us an R01 squared in the denominator. And then we'll have some R01 squared in the denominator. And so we'll have some other effects that we could use to really reduce this. All right. So the resultant expression that we have, so let me write that out, and then we'll play with it from there. I'm wondering if I should write this other form. Let me just write this out. Before I do this, I want to write it out and make one other assumption. So I knew I should have written this relation out, even though it was kind of simple. But when we do that, this obliquity factor substitution, we end up with u of, say, xy. Our observation point P0 that we have is, coordinates x and y. This is equal to z. All right, we've from that z there over j lambda, and then we have, again, this integral over the aperture u of psi eta. That's our P0, or P1 rather. And then we have this exponential of jk R01 over R01 squared d psi d eta. Okay, so the point I'm wanting to make here is that we have, so the reason why we're playing around with R01 is we have R01 in two places, right? We have R01 here, which is just a 1 over square factor, right? And we also have R01 here in this phase term, all right? So I'd like to make the following argument. The R01, the 1 over R01 squared, we can write that basically as just 1 over z squared, okay? Given our other assumptions that the aperture is small compared to that distance, you know, and our observation plane will also assume that that's pretty close to the axis. So again, we could substitute just for this 1 over R01 squared with a 1 over z squared, okay? Now, the reason we have to do all this other rigmarole over here is this one we can't just, you know, kind of discard in the same way. Why? Well, k, remember k is equal to 2 pi over lambda. So if we multiply k times R01, if R01 changes even a little bit, we're scaling it by, you know, like a micron, which is, you know, a millionth of a meter. And so any small change here is going to produce a large phase change, okay? So here we have to be more careful, or have a better approximation. And this is the better approximation, okay? This, using that binomial expansion term is the better approximation. Okay, so now we'll write the expression I was going to write. Okay, so using all that, we have then that we can say, substituting this factor with 1 over z squared. Of course, that comes out of the integral now, which is nice too. We don't have to worry about that because this is just the lateral dimensions in the observation plane. I'm sorry, in the aperture plane. So we have u of xy. This is the observation plane. All right, is now equal to e to the j kz over j lambda z, and then we have our integral minus infinity to infinity. The field u of psi eta, again in the aperture plane, and then we have the exponential of j k over 2z times x minus psi squared plus y minus eta squared d chi d eta, which are, again, the aperture dimensions, coordinates, right? So we're going to make some more simplifications, but before we do that, what is the form of this integral? Well, yeah, we'll get to that. Fourier transform was the comment that was made, but it looks a little bit more like something else that we just talked about. Right? Notice we have this shifting here going on. Right? We have basically a variable, a dummy variable that's going to be integrated out. So we have x minus chi there, and we have just chi and eta. So this is really a convolution, right? So again, so that's kind of a very useful thing to consider. We'll come back to that a little bit later. And if we can write that more explicitly in the following way, and we'll use this later again when we talk about some specific diffraction problems, all right? So here we have u of xy is equal to, again, this integral minus infinity to infinity, u of chi eta, and then the the other function that we have here is h of x minus chi, y minus eta, d chi d eta, all right? Where h, okay, h of xy is all this other stuff in, basically. So that's equal to e to the j kz over j lambda z. So all the z's come out of the integral. They're not part of that operation. Exponential of j k over 2z times x squared plus y squared. So there's kind of a quadratic function there. So again, so we have this convolution notion as well if we look at this function here in this form. All right, so now let's go back and let's expand this, all right, after that little diversion, which we'll come back to a bit later. Let's look at this expansion, or let's expand these squares here. So we now have u of xy is equal to the exponential of j kz over j lambda z times the exponential of jk over 2z. So we're just doing these squaring operations. So we have x squared plus y squared. From squaring those two, comes out of the integral. We don't have to worry about it in that form. And then we have all of this times the integral minus infinity to infinity. Here is u of chi eta e to the j k over 2z chi squared plus eta squared, and this is then times e, or e to the minus j 2 pi over lambda z x chi plus y eta, and this is integrated over d chi d eta. Okay, so before I say anything else there, notice that the integration limits, we started out with just integrating over the aperture, right? But now we go from minus infinity to infinity, okay? Any idea why I was able to do that?
Aperture is equal to 0.
Exactly. So the aperture, if we were to illuminate this aperture, right, we have, light that can go through the hole, but not, past the blockage, right? So we have this blocked area and we have the open space there. So that allows us, so since we're just going to be really integrating over the aperture, but we can extend it to infinity, which makes it in a nice form, which is now, as you mentioned earlier, so what we have here, this is a Fourier transform. But it's the Fourier transform of the function that appeared in the aperture times a quadratic phase factor. All right, so we have this nice Fourier transform, but we have this, there's also, it's kind of like the field superimposed on a curved surface, right? A kind of a parabolic surface, right? This quadratic. So what does that do for us? Well, if we were to look at what happens if we allow this field to propagate, so here's, say, the aperture out here, and so we have some opening again out there, and then we go out to a distance z1, we might get a field that looks like, kind of a set of ring patterns here. So we have some intensity, and then there may be, say, a null in the middle of it, And so what we might see is something that looks like that, okay, out at a distance of z1. And then if we go another distance away, say z2, what will we get there? All right, well, what we'll get there is we'll get something different, okay? So here we may have something that looks like, we get a, maybe that's a little darker out there. So we'll get something that looks maybe something like that, all right? So the point is that because of this quadratic phase factor, okay, we get a varying phase that's being Fourier transformed, right? Because we're multiplying that by this aperture function, and so that varying phase keeps changing things. So when we're in, and so notice this is a very specific set of approximations that we've made to give us this result. All right, so when we have this case, when we have this quadratic phase factor times u, and we have the Fourier transform of that, giving us the diffracted field at our observation plane, and the consequence of that is a changing diffraction function as well as expanding function. We're in the Fresnel region, the Fresnel diffraction region. Or the near field. Okay? So again, whenever we say we're in the near field, it's going to have this characteristic where that function is progressively changing as we move in distance. And so this region is a certain propagation distance. If we go actually too close, we're not in the Fresnel region, right? And we can decide that because we made these very specific assumptions somewhere, one of these pages, yeah. Oh, here it is. We made these very specific assumptions here, particularly this binomial expansion, which we said that we can throw out this other term here and just have this 1 plus 1/2 b being adequate description for R01. So we're not going to be in the Fresnel region all the way to z equals 0. There we have to worry about, Green's functions and doing all kinds of other things if we really want to know what the diffraction field is right next to that aperture. But as soon as we get to the point where we can make that binomial expansion assumption, then we're in good shape for just using this Fresnel Fourier transform relation. Okay. Okay. So that's fine. So now what if we say, all right, so what if we go further, all right? So so this quadratic phase factor, we're kind of thinking about the dimensions of our of the aperture, right? This psi and eta relative to that distance z. Okay, so we basically have a relationship there where we have this k over 2z psi squared plus eta squared as a phase factor. All right. So what if we made this like these dimensions, or made the distance really large? If we made the distance really large, then this is going to be much less than 1 going to 0. And then this whole phase factor that we have, this e to the j k over 2z chi squared plus eta squared, that's going to go to 1 as well. All right. So in order for that to be true, if we rewrite this expression here, we see that z must be much greater than k over 2 times the kind of the maximum extent of this aperture, okay? And how far do we have to go in order for that to be true? Well, if we, for instance, if we took a, if we had a wavelength here about 0.6 microns, and we had a, say, dimension eta max here of about an inch, 2.5 centimeters, okay? And when we solve for z, that z is going to have to be pretty large. It's going to have to be greater than much greater than 1,600 meters, 1.6 kilometers, okay? So that's a pretty big optical table in order to really get into that. But that's a pretty big aperture. However, later we'll see that, you know, we could just use a lens and we can eliminate this problem of needing to go really far in order to be in the far field. Now, why is this far field so important or so interesting? Well, it's interesting and very useful because now our relationship for the field at the observation plane, again, Huygens principle, when we're in this condition here, is written as, we have these functions out, these phase functions, e to the j kz, e to the j k over 2z, x squared plus y squared. So we still have this other quadratic phase factor there. We'll deal with that later, over j lambda z. And then we have our integral minus infinity to infinity of u of chi eta, which again is the field in the aperture function, exponential of minus j 2 pi over lambda z x chi plus y eta, and integrated over the aperture d chi d eta. So, so again, what we have then is simply the Fourier transform of the field that's in the aperture. All right, so when we have that situation, so here we have the Fourier transform of u is the diffraction field. At z. And so now the characteristic of the far field is that the pattern that we have now, let's go farther out here. Okay, so that pattern is just going to stay the same regardless of what distance we go once we've reached this condition where this approximation holds. So the field is still kind of expanding, all right, but it's not changing function. So in this case, the diffraction field does not change its functional form. Okay, so that's very different from the Fresnel region, where you do have that changing, because you're, again, taking the Fourier transform of that function times the quadratic phase factor. Okay, so basically that's, you know, kind of the diffraction theory. So we have our Huygens principle, and then we have the Fresnel diffraction region, which is Fourier transform of the aperture times a quadratic phase function. And then we have the far field region, or Fraunhofer region, where the diffraction field is the Fourier transform of just the aperture function itself. Okay? And most of the time, or in most situations for this class, we're just going to be worried about the far field. Okay? And later I'll show, you know, derive very simply and relatively quickly how, you know, why we can utilize this in the lab just by simply using a lens to do that operation for us. So before I do that, I want to look at a couple of very simple aperture functions. So I'm sure, again, so I apologize to the Op Sci students who've probably seen this many times, but we have kind of a mixed group. And again, I just want to go over a couple of apertures that are going to be very helpful in the class. So one is a rectangular aperture. Square is a special case of a rectangle. And so again, we have our coordinates psi and eta, and we have a rectangle with dimension wy in the eta dimension and wx for the half aperture here in the chi direction. And we'll illuminate this with a normally incident plane wave. We could change that if we like later and deal with that as well. But for now, we'll just do a normally incident plane wave, NIPW. And so our transmittance function that we have in passing through this, the transmittance function for that aperture is T sub A of chi and eta is just again, so we have a rectangular function of chi, and again, we'll use that scaling or similarity relation that we talked about earlier, chi over 2wx, right? So that's twice the width there, and rec of eta over 2wy. Okay. So if we want the far field diffraction pattern, what we need to do is to take the Fourier transform. So what is the field? Well, the field, if we come in with a normally unit amplitude, normally incident plane wave, u of chi eta is just equal to T sub A of chi eta. All right. So the far field pattern then we get by, so we have u of xy very simply is all of this stuff here. So we have carry that around, e to the j k z, e to the j k over 2z, x squared plus y squared over j lambda z, and then all we have to do is take the Fourier transform of u of chi eta. All right, and we can put this in terms of, instead of x and y, we can put it in terms of, since we're doing a Fourier transform, let's put it in terms of the spatial frequencies, fx equals x over lambda z, and fy is y over lambda z, where x and y are the coordinates in the observation plane. All right, so the Fourier transform, of course, of a rect function is a sinc function. So we have Fourier transform of u of chi eta is just equal to a function, again, using similarity, right? So we have 2wx times 2wy. That's just the area of the aperture. So we have a 4wx wy in this case is equal to the sinc of 2wx fx and sinc of 2wy fy. All right. And running out of paper. A little bit left. Okay. So, what? I'm good for a little while. Maybe I'll run out of time in the meantime. So, 4, 5. Okay. Okay. So the functional, or that's our, so in order to get u, then all we have to do is multiply this times that. I won't do, let's just call that c, sort of complex, times this Fourier transform of t sub a, which is this. And that's going to be, again, equal to our u of xy. If we want the intensity function I, which is usually what we'll be able to measure, that's equal to this magnitude squared. And so fortunately now a lot of those phase terms drop out, and we're just left with a squared, area squared over lambda squared z squared times the sinc squared of 2wx. I keep going back and forth between frequency, x over, between frequency and space, x over lambda z, and sinc squared of 2wy y over lambda z. Okay, so that's our relation, and then the plot of that, very simply, is this sinc squared function. So that's 1 unit, 2 units, and so forth of, say, if we're plotting in the x direction, 2wx x over lambda z. So these have units of, when that function is equal to 1, we have that, and of course it's on both sides like that. All right, so again, very useful aperture, in optics is a rectangle. Another example too here is if we have a circular aperture. A lens, an iris, a circular beam illuminating a hologram. All of these have circular function, so this again is a very useful one. And so here we have our circle, like so. We come in with a normally incident plane wave, and here we have to do something a little different. So we'll take kind of radial coordinates, and we'll call that q for the radial coordinate, and the maximum radius is w here. So here we can write a transmittance function, again with a normally incident plane wave, unit amplitude. Our transmittance function t sub a of q is, we can write this as a standardized function of a circ function of q, again scaled by the radius w, all right, where q is equal to square root of chi squared plus eta squared. Okay, so now we want to, again, so our kind of process is the same. We're going to need the Fourier transform of this circ function. But the circ function is in these radial coordinates. So what we end up needing to use is a Fourier-Bessel function, or a Fourier-Bessel transform. So here we have u of r, the radius function in the observation plane. This is our diffracted field here, is equal to e to the j kz over j lambda z times exponential of j k r squared over 2z, 2z. And we have this kind of Bessel function, or Bessel Fourier transform of u of our radial coordinates. Okay, so in this, the our transform variable that we're going to have is, and this is in terms of a function or a variable rho, which is the spatial frequency variable. Rho is equal to r over lambda z. And so r is the radius coordinate in the diffraction plane that we're looking at. So this is the radial or radius coordinate in the transform plane. And rho rather, is related to that, and that's equal to the square root of fx squared plus fy squared that are in Cartesian coordinates, okay, to show the relationship between those two. And so our field with this normally incident plane wave hitting this transmittance function again is just u of q is equal T of A of q, and this Bessel function that we have of Bessel Fourier transform function of the circ q over w is equal to, again, the area times a j1 2 pi w rho for the argument over pi w rho. All right, so we end up with this Bessel function of the first kind, this j1 function, and that, just finishing this off now, we can write our diffraction field. Again, this is in the diffraction or Fourier transform plane. This is going to be equal to e to the j kz times e to the j k r squared over 2z divided by j lambda z times the area. And then we could write this in the very well-known form where we have this is equal to 2 times j1 of k w r over z for the argument divided by k w r over z, or the 2j1x over x function, the Airy function, very well known. And again, in order to get the intensity, we square that. So we have a squared over lambda z squared times the 2j1x over x, 2j1 kwr over z divided by kwr over z squared function. And so remember I mentioned earlier when we were talking about the spectrometer that you get this 1.22 times lambda z over the radius, or 2.44 lambda z over diameter. This is where it comes from, because if we were to plot this here, we end up with, again, something that looks like direct, but the zeros occur at here at 1.22 and 2.33. Oops. Doesn't go below the axis there. Okay, and so this argument that we have here is 2wr, this is the diameter, over lambda z. So when this is equal to that, all right, we end up with a null, and the width of that function between those nulls, this is where the 2.44 comes from, right? Between those. And so we can write this as we have 1.22 is equal to 2wr over lambda z, which gives us r equals 0.61 lambda z over w, or this delta r between here, between those two nulls, is equal to 2.44 lambda Z over 2W, or the diameter, right? So D is equal to 2W. All right, so again, very useful function. When we did that spectrometer, that's where that came from. So those of you who are waiting and anxiously to find out where that came from, now you know. Okay, so one other thing too, I guess today they're having that seminar. It was postponed from last week because of the football game, but there's a pretty good seminar on some new developments in digital holography. I've heard it actually. It's a new faculty member here, Ewan McLeod, who's giving it, and he has some interesting stuff to show there if you have the time to stay. I think there's cookies for you too, and drinks, so little enticement. Okay, so I'll see you guys next week. Again, next Monday, 9 o'clock, we have the lab. Okay. Oh yeah. So where is the lab? Those of you who don't know where my lab is, it's in 249, room 249 in ECE. Which, if you go into the building, there's the elevators. If you head north or towards Speedway, make your first right, and I'm the last door on your left. Okay. So if you get lost, just tell someone, or ask. I'm not tell someone. Ask some, ask someone where it is. There's a little map there as well. Maybe we'll put a sign up too. So, anybody not know where it is? Okay. I may just hang out down there or something to direct people or whatever. Again, if you keep heading north, all right, and make and on your right there are two secretaries there, Anna and Nancy, and they'll be able to tell you where my lab is. Okay. So, okay. See you guys Monday or Tuesday, depending on things.